Vaporization. So vaporization is a transition from a liquid to a gas. Condensation is the opposite, transition from a gas to a liquid. So here we have an illustration of a beaker full of water molecules. These water molecules are moving. They have thermal kinetic energy. The book describes it as a wild dance floor. So these guys, they're gyrating, they're wiggling, they're shaking it, they're moving around, right? Think of a crowded dance floor. What's holding them together? Dipole-dipole forces, hydrogen bonding, and dispersion forces. The intermolecular forces are holding them together. How can they escape into the gas state? They would have to have enough energy to break loose, right? Because we know that water boils at 100 degrees Celsius, but we also know that if you have water at room temperature, it will slowly evaporate, right? So some of those water molecules are getting into the gas state. So the ones that have enough energy to break loose can go into the gas state, even at room temperature or colder. So my analogy for this is a game we used to play in elementary school called Red Rover. Did you guys play Red Rover? They don't let kids play Red Rover anymore. So if you're not familiar with Red Rover, you'd have two groups of kids on opposite sides of a field, and each group of kids would hold hands, make one big long line, and then you call to the other team, Red Rover, send Susie right over, right? And then Susie comes running across the field at this line of kids and tries to break through, right? And so, you can see the potential for injuries, right? People breaking wrists, all kinds of stuff. So they don't let them do that.
What was the point again? I can't remember.
The point was to break through the line.
What happens if you didn't? Like, how do you win?
I don't think it ever went that far. I think if you break through, then you get to join that line, and pretty soon everybody's on one side or something. I don't know. A lot of children's games don't really have a clear point to grown-ups. It's just fun to try to, run at people, right? Anyway, so the Red Rover line are the molecules at the surface here. And these are molecules that ran at the Red Rover line and had enough energy to break free. Because if Susie comes at your line and she's just walking, is she going to get through your hands? No, she doesn't have enough kinetic energy to break through. What if you've got a bunch of kindergartners playing Red Rover? Is it going to be easy to break through? Yeah. A grown-up might be able to just walk quickly and just, plow through them. What if you've got the O-line of the Fresno City College football team? No, you're going to have to run much faster to get through, right? So strong grip, Fresno City College football players, strong intermolecular forces. You need a lot more energy to break loose. You need a higher temperature to break loose. Does that make sense? Weak intermolecular forces, easier to break through. Remember that the particles in that liquid have an average kinetic energy that's related to their temperature. But within that average, you have some that are above average and some that are below average. So this graph showing the fraction of molecules with a particular energy versus the energy, kinetic energy, here we see in this blue curve here at low temperature, the average kinetic energy is relatively low. This dashed line represents the amount of energy needed to escape. This is how fast they need to be going to break through the Red Rover line. So there's just these guys, this area here, that are able to break free. If we increase the temperature of the liquid, we increase the average kinetic energy, and now we have a larger number of molecules that have enough kinetic energy to break loose. So evaporation will be faster at a higher temperature. And we know that from everyday life experience. Why does your dryer heat your clothes? Why do we need heat? To dry them faster, right? Water evaporates faster at higher temperatures. So if you want something to dry quickly, you don't stick it in the refrigerator. It'll dry more slowly in there because the temperature is colder. It might never dry. Yeah, that's true. Okay. Another way to increase the rate of vaporization is to increase the surface area of the liquid. So in order to get from the liquid into the gas state, the molecule has to get to the surface, right? And so if it can't get to the surface, it can't evaporate. If we spread this out and make a large surface area, then more of those higher energy molecules are going to be able to get out. So which will evaporate, pardon me? Right. So if you take a glass of water and set it on the counter, and you could try this at home if you have a house where somebody's going to let you make a little bit of a mess. Take 2 cups of water, spill one on the counter, and set the other one next to it. And then notice how many days it takes for the water to evaporate, right? The water on the counter is going to evaporate much more quickly than the water in the cup. The water in the cup is going to take days and days and days. The water on the counter, depending on how warm your kitchen is, it might be gone in a day, right? Because it's higher surface area. If you have high intermolecular forces, strong intermolecular forces, then the rate of evaporation is lower. So we have 2 terms, volatile and non-volatile. Volatile liquids are liquids that vaporize easily. They have weak intermolecular forces. Non-volatile liquids do not vaporize easily. What if you spread some vegetable oil on the counter? How long would it take for that to vaporize? Probably forever, right? It just doesn't evaporate well at all. But acetone or alcohol, like we did the paper chromatography, and you pull that paper that's wet with acetone out, and you can see it get dry, right? It evaporates just like that. Acetone has weaker intermolecular forces. Well, let's think about the energy that's going on, energy transfer that's going on when things evaporate. So we had that beaker of water. Let's imagine that it's thermally insulated, so it's not going to be affected by the temperature outside the beaker. As the water evaporates from the beaker, is it the high energy particles or the low energy particles that leave? It's the high energy particles. So if you have all the high energy particles leave, what does that do to the average energy of the remaining molecules? It lowers it. Lower kinetic energy means lower temperature. When water evaporates, it reduces the temperature of the remaining water. Now, we can't always notice that because there is thermal energy transfer from outside. But as things evaporate, it's a cooling process because vaporization is endothermic. Energy goes into basically what's being vaporized. And we observe that, and our bodies utilize that in that when we sweat, and especially if a breeze comes by, it feels cool, right? Because the hotter particles, the higher energy particles are the ones that vaporize, and what they leave behind is cooler. And so it takes heat away from your skin. So vaporization is endothermic, condensation is exothermic. With these state changes, usually one of them makes sense, and the other one you're like, we don't think of water condensing as being something that gives off heat, and yet it does. So if you remember that vaporization is endothermic, another way to remember that is, well, if you want something to evaporate faster, you're going to heat it, right? You put energy into it, it will vaporize faster because it's an endothermic process. So then condensation, the opposite, has to be the opposite. It's exothermic. Steam can cause very, very severe burns because when the steam interacts with your skin, that water in the gas state, which is very high energy, collides with your skin and releases energy and causes significant burns. This whole Energetics of Vaporization and Condensation thing moderates temperature. So we see daily temperature variations are lower in regions with higher humidity because the water in the air absorbs and releases heat. So I pulled these up from the internet yesterday. Here's average daily temperatures in July for Fresno and for San Francisco. So we've got average high 96.6 here in Fresno, 68 in San Francisco. Lows of 66 and 54. What's the most significant, I think, is the temperature difference from the high of the day to the low. 30 degrees in Fresno, 13.8 degrees in San Francisco. It's not just that it's cooler there. The temperature just doesn't change as much. And that's due to all the water around San Francisco. You have the ocean, and then on the other side of the peninsula, you have the San Francisco Bay. And because of all that water, the air is also going to be more humid. So during the day, as the sun's rays hit the earth, the water absorbs the energy. Some of it evaporates. That keeps it from getting as hot as it does here. Then at night, when the sun goes down, water condenses, and as it condenses, it releases that energy back. Question?
So an island then has like, no temperature change?
An island would have less temperature change, yeah, generally speaking. So, here in Fresno, in the summer, it doesn't rain. And yeah, we have some irrigation and stuff, but the humidity level in the air is very low. And so the sun heats things up. And as soon as the sun's gone, it cools down.
So places on the East Coast, like Washington, D.C., they get so humid because they're close to water?
It's not just proximity to water. I grew up in Minnesota and Iowa. Iowa does not have many lakes. It is not next to an ocean or anything, and yet the humidity there is unbelievable sometimes. The day we got married, it was 95% humidity and 95 degrees. Sweating does no good.
Or like Southern California, you're next to the ocean, but it's not very humid. It's pretty dry.
Yes, but the ocean is still right there, and it absorbs, so it does moderate temperatures. Like you go into the desert, and really Fresno is a desert, right? Or you go into, like Death Valley, and everything just absorbs the energy from the sun, and then when the sun goes down, it gets really cold at night. So water moderates our temperatures.
Isn't it better to live in humid environments though? Like good for
I
your
think,
skin?
well, that's a matter of personal preference. For some people it matters, and other people it doesn't.
So because of water, there's not much temperature difference in San Francisco.
Right. Yeah. The weather in San Francisco is pretty boring. Which, well, yeah, it's nice unless you want to go swimming. It's pretty much always too cold to go swimming. We lived in the Bay Area, and the complex we lived in had swimming pools, but there were very few days when it was actually warm enough that you would want to go swimming.
There's this dolphin group in San Francisco, that's what they're called.
Mhm.
And they put on wetsuits and they just go swimming. And
Mhm.
they go all the way to Alcatraz and turn around.
Cool.
I think it's insane.
It is insane. When you have a wetsuit on, that wouldn't be so bad, but there are also people that just go swimming in the cold water. Yeah. It can be dangerous.
There's a lot of sharks in that bay too.
Well, there's sharks too. So, of course, we can quantify the amount of heat energy change when we vaporize things. So the heat, or the enthalpy of vaporization, delta H, is the amount of heat needed to vaporize 1 mole of liquid at its normal boiling point. It's always going to be positive. I know, here's more math, sorry. So it's always going to be positive because you have to put energy in to vaporize. There's a little bit of a temperature dependence, but it's not real significant. At the boiling point, at 100 degrees, the heat of vaporization for water is 40.7 kilojoules per mole. At room temperature, it's 44. So it changes a little with temperature, but not too badly. You do not have to memorize this table. If you need heats of vaporization, they would be provided to you in some fashion. So if water absorbs 40.7 kilojoules per mole when it evaporates, it must release that when it condenses.
Oh, can you have temperature in a vacuum? Or do you need to have like something?
Can you have temperature in a vacuum? That's a good question. I think in a perfect vacuum, no. Because temperature is the average kinetic energy of the particles, and if there are no particles, then there's no kinetic energy.
So there's no matter, there's no mass?
In a perfect vacuum, there is nothing.
How do we create that?
Well, I'm not sure if you can make a perfect vacuum. You can get close, but I don't.
Isn't that just like time capsule, just pure time? There's no matter, it's just time.
It doesn't matter. And we're running out of time. So we're going to go on. So the heat of vaporization is just opposite in sign to the heat of condensation. So when you condense the gas back to a liquid, it releases the same amount of energy. Yeah. So we can do problems like this. Calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. So like many problems that we run into in this class, we can actually treat this as a unit conversion problem. And so they're asking us to find heat in kilojoules. And they're giving us 2.58 kilograms of water. And so we need to figure out how to get from the beginning to the end.
Convert that to
We can convert this to grams, yeah,
Grams to moles then?
grams to moles.
And moles to photodensity ratio.
Well, we don't have a chemical reaction going on. A chemical reaction means that a substance is destroyed and a new substance is formed. All we have going on is a change in state. So there's not going to be a mole-to-mole ratio. Vaporize, maybe the heat of vaporization would be a useful thing.
I would think that, but we don't know how much heat it takes to heat up one mole, vaporize one mole.
Well,
It's gotta be, is it a constant?
it's a constant.
Isn't that like
We go look it up in the table.
Oh.
For water,
like
at the boiling point, 40.7 kilojoules to vaporize 1 mole.
Okay, so you know how you just said, like I get the chemical reaction when someone undergoes a chemical reaction, a new substance is produced.
Mm-hmm.
But what about when chemical reactions are irreversible? Does that still make it,
That would still be a chemical reaction, yeah.
even though it can go back and forth? both
Oh,
ways?
reversible. Yes, it's still a chemical reaction. Because bonds are being made and broken,
So
and
you-
the substances are changing.
If you could cook a piece of meat and then put it back in the raw form, and it's back and forth.
No, because that's denatured.
Well, you can't do that.
Yeah, no, I know you can't.
But
if you could-
there are a lot of chemical reactions that are reversible, but they're still chemical changes. What we're talking about here is just a state change. So the individual particles are not changing. What's changing is how they relate to each other. So in a liquid, they're kind of stuck together, but able to move around. And in a gas, the particles themselves have not changed at all. They've just been separated. So it's not a chemical change. But yeah, you're right. We didn't know the amount of heat to vaporize a mole, but we go look it up in the table. 40.7 kilojoules per mole. So that means that we can go from moles to kilojoules. So we have that 40.7 kilojoules per mole. That's a conversion factor. Anytime you see a unit that has per in it, something per this, moles per liter, grams per mole, kilojoules per mole, that's a conversion factor. Okay, so 2.58 kilograms of water, and we're going to go to grams of water. Remember, just stick all the units in there first, and then we're going to go to moles, and then we're going to go to kilojoules. That's the path I decided on. And then kilograms becomes the denominator for the next term. If you still haven't quite gotten the hang of dimensional analysis, it's not too late. Here we are using it again. So the moles cancel, the grams cancel, the kilograms cancel. You can put the numbers in. You can take care of these terms in whatever order you want. I'm going to do this last one first. 40.7 kilojoules per mole. The 40.7 goes with the unit kilojoule. And if we really want a number in the bottom, it's going to be 1. 1 mole of water requires 40.7 kilojoules. How about this first one? As I'm grading labs, I'm really dismayed by how many students are doing simple metric conversions backwards and telling me that, 15 milliliters is 15,000 liters or something like that. Okay, just stop and think about it for a minute. Don't take your thinking cap off when you do problems. What does kilo mean? 10 to the 3. So I've got kilo in the bottom. I'm going to put what it means up here. So I'm multiplying, right? And then how do we do this grams to mole thing? The molar mass of water. 2 times the mass of hydrogen plus 1 times the mass of oxygen. It's 18.02 or 0.16. 2.58 times 1 times 10 to the third divided by 18.02 times 40.7 equals, and my calculator is saying 5827.19 kilojoules. How many significant figures should that number have? 3. So it's okay to call this 5830 kilojoules. But some people lose their minds and call it 583 kilojoules, which is not the same. The best answer is 5.83 times 10 to the third kilojoules. That's the best answer. Any questions? Bless you. So we looked at what happened when water evaporated from a beaker. What if the container has a lid on it? Here's an Erlenmeyer flask with a rubber stopper.
Eventually you won't be able to evaporate anymore.
Right, eventually it can't evaporate anymore because it'll fill up this space. So initially there's just air up here without any water, and because it's not humid here. And so the water begins to evaporate. As the water evaporates, what do gas particles do? They travel in straight lines until they hit something, right? And so these guys are going to come up here and they're going to bounce around, and eventually they're going to hit the surface again and they're going to condense. They're going to get trapped. So we have things evaporating and we have things condensing. The rate at which the evaporation occurs just depends on the temperature and the surface area. In this flask, the temperature is not changing significantly. The surface area is not changing significantly. So the rate of evaporation is fairly constant. Question?
This might be a silly question, but why can't we hear them? Because, say you had some, heated water in a big container or something, and it was sealed off. Since there's so much of it, why can't you hear it?
Why can't you hear the gas molecules hitting the walls?
Yeah.
I think because they're just too small. So, what flashed into my head was Horton Hears a Who, right? So Horton Hears a Who, there's this little tiny planet. It's a dust speck, right? And he's got it on this clover, and he's got these ginormous ears, and he can hear them. But nobody else can hear them because their sound is just too small. Yeah. Or maybe we can hear them, and it's just so constant like the air pressure that we don't even notice it. I don't know. That's something to think about when you wake up in the middle of the night. So rate of evaporation in this situation is going to be constant. Initially, though, there's no condensation because there are no particles up here. The more particles we have in the gas state, the faster we're going to have condensation, right? The rate of condensation depends on the concentration of gas particles. The concentration of the gas particles is related to the pressure of the gas particles. Does that make sense? So eventually we're going to get to a point where the rate of evaporation is equal to the rate of condensation. The number of gas particles in that flask is going to be relatively constant. But it's not the same gas particles. Okay? It's a little bit like a busy airport. If you counted the number of people inside the airport at 10 a.m., and you counted the number of people inside the airport at 2 p.m., it'd probably be about the same number of people, right? You have airplanes leaving, taking people away. You have other airplanes coming in, bringing people in. You have people leaving to their cars, and you have people arriving to get on airplanes. It's different people, right? But the same number of people. It's different molecules in the air, but it's the same number. Does that make sense? It's called a dynamic equilibrium. You have the process of evaporation, you have the process of condensation. They're happening at the same time and at the same rate. And so overall, it looks like nothing's happening when actually they're both happening at the same time. Or it's like a busy freeway where you have cars going north and cars going south. And if you counted the number of cars at each end, it'd be the same over time, but it's different cars. So the pressure that the gas exerts is called the vapor pressure. So vapor pressure is the pressure of a gas in dynamic equilibrium with its liquid. So anytime you have a closed container that has a liquid in it, you're going to have a vapor pressure. We learned about the vapor pressure of water when we dealt with gases and collecting gases over water. And so the water evaporates and it forms a pressure in the container. The vapor pressure is going to depend on the intermolecular forces because the rate of evaporation depends on intermolecular forces. The rate of evaporation will be higher if the intermolecular forces are weak, right? It also depends on temperature because at high temperature, more particles have enough energy to escape. So initially we see that there is no condensation. Here's the rate of these processes over time. The rate of evaporation is going to be constant. The rate of condensation will increase as there's more and more water in the gas state until it gets to the point where it equals the rate of evaporation. Because now 5 particles evaporate, 5 particles condense. The concentration doesn't increase, so the rate of condensation is the same.
Well, if you had that container, closed container, and the liquid evaporated, if you shook the container, it would condense, all would condense?
Well, it's not all going to evaporate. It will evaporate to a certain point. If you shake it, there might be an initial disruption of the equilibrium, but it will quickly return to the same state.
It'll stay as liquid or go back to being vapor?
Well, there's going to be both present, and there will still be both present if you shake it. Now, shaking a can of soda is completely different, but just shaking, a pure liquid won't do anything really. So here we have a piston. We've got a liquid in here. Looks like it might be, pentane or something. And it's evaporating and condensing, and so we have an equilibrium here. This substance in the gas phase has a vapor pressure, and so there is a certain pressure being exerted by the gas. If we expand the volume of this container, what does that do to the pressure of this gas? It decreases it. Le Chatelier's principle says that a system in dynamic equilibrium will react to a change to minimize the change. So the pressure decreases. That decreases the rate of condensation. Evaporation continues, but the rate of condensation has decreased because there's fewer particles in the volume. The volume's larger, right? And so evaporation will continue until they become equal again, and the pressure will go back to what it was over here, even though we changed the volume. So you increase the volume, and it takes a little bit of time, but the vapor pressure will return to the same value it had before. Then if you take that plunger and you push it down and make the gas volume much smaller, now you increase the pressure of the gas, or the concentration of the gas, and you increase the amount of condensation. And so a lot of these gas molecules will go back into the liquid and not escape again until it equilibrates again, and you end up with the same vapor pressure. Any questions? The vapor pressure depends on temperature. Oh, we're running out of time. I'm going to stop here, actually.